Now, before studying the integral, you need to be familiar with concepts like limits and continuity, as well as differentiation or the derivative, which I have videos on at my channel, and you can check them out. And I highly suggest you do before watching this video. Now, the integral is the approximation of the area between the x-axis and a function's output. Now, you might hear quite frequently that it's the area under the curve, and while that is the case sometimes, you could have a function that looks something like this. And that function, if we were to find the area from right here to right here, so from boom to, let's say, -1 to 1, that area is actually above the curve. It's not below it. So when you hear the phrase beneath the curve, that doesn't actually apply here. It applies here and here. Those are above the curve or below the curve, but not here. And so this would actually, when it's above the curve, it's actually a negative area. And when it's above the x-axis and below the curve, it's a positive area. But it's just an important nuance that I thought I would point out. Now, what do we really mean when we say the area above or below the curve? Well, it's actually the limit. Remember, we got to reference limits. The limit of the Riemann sums. And now you're probably wondering, what are Riemann sums? Well, Riemann sums are rectangles we would use to approximate the area under a curve. So we use a geometrical shape, such as a rectangle, as many as we can fit underneath the curve to estimate its area. And so we could actually fit an infinite number of rectangles under any curve. And so in order to overcome this idea of infinity, we use limits. And what we mean algebraically of the area, we would write the limit as n approaches infinity of the Riemann sums. So we have our summation symbol. So the index will equal 1 for n terms of the function of a given function f of x and I, f of x I, so each x that changes. And we do this times dx, which is infinitely small, and I don't want to tackle the problem that is infinity, because infinity is not a number, but dx is equal to the change in x, or equal to b minus a, and this is an infinitely small value when taking the limit towards infinity. Now this entire expression is the integral, but Leibniz devised a way to write it in a way that is more impactful, let's say, more useful and easier to understand. He says that this part right here is the same thing as this symbol, this stylized S. And then we can take this part and throw it in here, f of x dx. Now technically I kind of broke it up just so we could see it, but technically it would include this part too. But so f of x dx is equal to the limit as n approaches infinity of Riemann sums. These are the same thing for a given function f of x dx. And so we have the integral. And the integral brings us to what we call let's do it in this color. The integral brings us to what we call the fundamental theorem of calculus. And with the fundamental theorem of calculus, we get some interesting outcomes. The fundamental theorem of calculus breaks up into two parts. Part 1 says that if we have an integral that is equal to capital F of x, this is a capital F of x, by the way. Capital F of x, which is equal to our integral, f of x dx, then we could take the derivative of it, derivative of capital F of x, and we get our original function f of x. Now, why is this the case? This is the case because this expression here is what we call the antiderivative. This is the antiderivative. So anytime we applied the derivative properties, we could do the reverse of those and get back to this integral. And this integral represents the antiderivative, which is interesting. But the second point, or the second part of the fundamental theorem of calculus, tells us that if we had a definite integral instead of an indefinite integral like we've seen so far, a definite integral has an upper and lower bound. Let's say the lower bound was a and the upper bound was b. We could, of a function f of x, we could find the antiderivative at b and subtract it from the antiderivative of a. We are finding the difference between these two antiderivatives at each boundary, and we get the integral as well, or the area between the x-axis and the y-axis, or the x-axis and the function. Those are the two steps of the fundamental theorem of calculus, and as we will see moving forward as we apply this framework that I have described here, it is very interesting to see how we can rearrange expressions, rearrange equations in order to find what we are looking for, especially an area under the curve, which can be useful across many, many different sectors and industries and have many applications. So with that, let's jump into a problem or an example which uses many, many integration properties, many integration mechanics in order to get a better understanding of the concept. Let us imagine we have a function or an integral. Let us imagine we have an integral with a lower boundary, so a definite integral. We have a finite space along the x-axis with which we want to identify the total area. And the upper boundary we will say is 4. And the function we have will be x to the 4th plus 2x squared plus 5x all over x dx. So what's the first thing we want to do? Well, what are we aiming to do first of all? Well, let's identify the area. Let's evaluate this integral. Evaluate the integral. So we want to find that area between the x-axis and the function's output between 2 and 4. And so to do this, we want to identify the antiderivative. Evaluate. What is the antiderivative? To do this, we should, just by looking at this equation, I think we can rewrite it or simplify it so that we can more easily perform the reverse power rule. So we're going to be using the reverse power rule in this. And I haven't covered that, so that is something you will have to look up, or I can just tell you actually. So it's just, imagine we have x to the fourth. We would just add 1 to this, the antiderivative, over 4 plus 1. So the antiderivative of x to the fourth is really x to the fifth over 5. And so we want to rewrite this. So we are looking at the integral from 2 to 4, and we can rewrite this as x to the fourth over x plus 2x squared over x plus 5x over x. And that tells us we could rewrite this again as x to the third plus 2x plus 5. Now this is a much easier expression to find the antiderivative of. And if we bring it up here, we get, so the reverse power rule of x to the third would be 1/4 times x to the fourth plus the reverse power rule of 2 to the x. So imagine it's x to the 1 power. Now it's going to be x to the second power over 2, which is just 1. So x squared plus, imagine that this is x to the 0 power. So now it's going to be 5x plus 5x. And there is our antiderivative. And we would be done if this was an indefinite integral, but it is not. We have an upper bound and a lower bound of 2. So we need to plug those in using that second part of the fundamental theorem of calculus, which said that capital F of B minus F of A gives us what we want for this definite integral. So we will plug it in, and we get 1/4 times 4 raised to the 4th power plus 4 raised squared plus 5 times 4 minus 1/4 times 2 squared plus 2 squared plus 5 times 2. Boom. And what is all of this? I need a calculator. I have one by me. So I went back and checked my work to see where I was making a mistake, and I actually found it not as quickly as I'd like to admit. That's why you should probably not do math late at night. But this 2 is actually got to be a 4. So if we erase this and make this a 4, we get 2 raised to the 4th power is 16 divided by 4 is 4. So minus 4 minus another 4 minus 10. And that's minus 8. That's minus, I don't know what's going on. Minus 18. and that equals 82, which is the answer. The area below this function, I believe this is a positive, so between the x-axis and the function, the area from 2 to 4 is 82 units, whatever those units may be. And now let's find the derivative of this expression. So we have here, I think this is in its simplest form before I found the antiderivative. We had a function x to the third 2x plus 5. And so we want to find the derivative of this expression. So we would do the derivative properties, so the power rule. This will be 3x squared plus 2, and 5 goes to 0. So this would be our derivative formula. Equation, excuse me, not formula. And so now we have the instantaneous rate of change of this integral function. And so what if we plugged in a number? Let's say, what is f prime of 3 equals 3 times 3 squared plus 2. And that equals 3 squared is 9 times 3 is 27 plus 2 equals 29. So 29, is our answer. Now let's look at what these really mean by looking at a graph of these expressions and give them units, give them arbitrary units that, honestly, this is just a random function, so it'll just have no relation to the actual real world application, but nonetheless it will give us a way to conceptualize it better. And so here is a visual representation of this integral, this definite integral. The graph looks right here, and we can go from 2 to 4, which is the lower bound and the upper bound, as you can see here. And this area that's shaded in purple is 80, that area underneath the curve. Now, there are no units here, but if we could imagine it for a moment that this is we could pretend, I should say, that this is a curve for, let's say, Bitcoin mining. And this x-axis, is the unit t, so time. And the y-axis here is actually going to be the hash rate. In other words, this is the hash per second. And at 2, let's say 2, and so we can interpret this to mean that over, let's say 2, we'll call it, let's say 2 weeks, over a 2-week period. So let's say t is in weeks, and this is week 2, and this is week 4, and so this is a 2-week period. Over that 2-week period, there was a total of 80 hashes, and then instead of just saying hashes, let's say it's exahashes that were performed or computed during Bitcoin mining. 80 total exahashes. And that is the value of what this solving this gives us. And obviously we can apply it to more than just Bitcoin mining. There are endless amount of applications for this. The important point to note is that that y-axis has to be a rate. So some kind of rate, not just hashes over here. And when we found the derivative, we actually found at 0.3, so 1 week later, the actual rate of change at that given point. So we found the slope of the tangent line right here. And I forget what it was. I think it was 29. It was 29. And so this is actually 29 hashes at 3 weeks, which looks about right. So this is all calculus coming together, which is really interesting and cool. So with that, I'll see you guys in the next video.